Recommendation systems are one of the most fascinating applications of machine learning. Sites like YouTube or Netflix use them extensively to recommend us movies and videos that we may want to watch. In this video, we're going to focus on the following question. How do these work? So one method they use a lot is called matrix factorization. So that's what we're going to learn today. My name is Luis Serrano, and you can find me on Twitter at LuisLikesMath. This video is actually joint work with Janet Interian. She's a professor at the University of San Francisco, and she wrote a really nice IPython notebook that will accompany this. The link is right here, but it's also going to be linked in the comments. So let's get started. Let's say we have a Netflix universe, and in the Netflix universe, we have 4 people: Anna, Betty, Carlos, and Dana. And we also have 5 movies, movies 1, 2, 3, 4, and 5. And the users are going to assign ratings to the movies from 1 to 5 stars. And the point is we're going to try to predict these ratings. So let's say that Anna rated movie 5 with 4 out of 5 stars. So we're going to record that in this big table on the right where the rows are the users and the columns are the movies. We're going to record this 4 in here on row Anna and column movie 5. So we do that for every user and every movie, and we get something like this. And now I'm going to ask you a question, and I'd like you to ponder on this question, so feel free to pause the video. The question is, how do humans behave? So I'm going to show you 3 tables. There's table 1, table 2, and table 3. And let's think, which one do we think looks more like the real Netflix table? So let's analyze them one by one. Let's look at the one on the left where every user gave every movie a rating of 3. So that was not very realistic. It's kind of assuming that all humans have the same preferences and also that all movies are rated the same by every human. So humans have a little more free will than that. So that was not the one. Now let's look at the third one. The third one is made by all random numbers. So that one basically assumes that all humans are completely different in terms of preferences and that all movies are completely different in terms of ratings by humans. And that one's also not very realistic. It turns out that this table has a lot of dependencies. Humans sometimes are similar to each other and movies sometimes are similar to each other. So it turns out that the table that is more realistic is the one in the middle. So let's study the table in the middle a little more. This table, which at first looks a little random, turns out to have a lot of dependencies. And again, feel free to pause the video and try to find as many dependencies as you can in this table. So here's one. If you look at the first and third rows, they are the exact same thing. And what does this really say? Well, it says that Anna and Carlos have very similar preferences. So for Netflix purposes, they are treated as the same person. So we can say that A equals C in terms of preferences. Now, can we find other dependencies in this table? Let's look some more carefully. Well, it seems that column 1 and column 4 are exactly the same. And what does that mean? That movie 1 and movie 4 are the same movie? Well, maybe not the same movie, but maybe they are very similar movies and people gave them similar ratings. Maybe movie 1 is Small Cop and movie 4 is that movie with Seth Rogen about a cop in a mall. So those things could happen too. We could also have dependencies among columns. But let's see, there are some more hidden dependencies. Let's look at this one between these 3 rows. Can you find a dependency among these 3 rows? So the dependency is the following. If you take the values in the second row and add them to the values in the third row, you obtain the values in the fourth row. So you can see that 1 plus 3 is 4, 2 plus 1 is 3, etc. And what does that mean? Well, it's kind of strange. It's like saying that the preferences of one person plus the preferences of another person are the preferences of a third person. But this could happen. Maybe Betty loves action movies and Carlos loves comedy, and Dana just happens to love both comedy and action movies. And when it's a comedy action movie, then Dana loves it. So it's kind of like you have 2 people and then a third person with the preferences of the other 2 people together. So it could happen, and we could have dependencies like that. let's see, are there any more dependencies? Let's look at this 3 columns over here. So if you look carefully, the column number 5 is the average of columns 2 and 3. As you can see, the values, for example, the 1 and the 1, the average is 1. The 2 and the 4, the average is 3. And how could this happen? Well, what if movie 2 is Twister, so it's about a tornado, and movie 3 is Jaws, which is about a shark, and movie 5 is Sharknado, which is about tornadoes and shark. Well, I mean, it could be that if you like tornadoes and sharks, you're gonna like Sharknado, and if you say you like tornadoes but you hate sharks, then you're just gonna be okay with Sharknado. So in some way, Sharknado is the average of Twister and Jaws in terms of ratings. Now these relations, they look a little too fake and a little too optimistic, and maybe they are, but at the end of the day, there are relations between columns and there are relations between rows that sometimes one can explain in terms of features and preferences, and sometimes we can't, but we still use them. And so basically what today's video is going to be about is this table has a lot of dependencies, and we're going to use those dependencies to guess ratings. So let me show you a very simple example of how to use dependencies to guess ratings. Let's say we have the super simple table where every user has the same preferences and every movie is the same, but Carlos hasn't watched movie 4. So what do we guess that Carlos is going to give movie 4? Well, this is very simple. Since everybody gave 3 to all the movies, then we're going to say that Carlos is going to give 3 stars to movie 4. So that's very simple, but let's go to a slightly more complicated one. And here, Carlos hasn't seen movie 5. So what do we think Carlos is going to give movie 5? Well, we remember that Anna and Carlos have the same preferences for everything because their rows are pretty much the same. So it's safe to assume that Carlos will give movie 5 the rating that Anna gave, which is 1 star. So now this is very simple, but we can do some math to actually guess some more complicated ones. So the question is, how do we figure out all these dependencies at the same time? And the answer is with matrix factorization. So why is it called matrix factorization? What is factorization? Let's remember some time in life where we saw something called factorization. Well, when I think of factorization, I think of something like this. 6 times 4 equals 24. So the 24 is a big number, but we express it as a product of 2 small numbers, 6 and 4. So we managed to break down a big number as a product of 2 small ones. And that is matrix factorization. We have a large complicated matrix at the right, and we're going to express it as the product of 2 things, like this and a that. And those 2 things are going to be small, like the 6 and the 4. And magically, they're going to give us that big matrix on the right. So we're going to have a much simpler scenario with 2 small matrices that multiply to the big one. And so now I'm going to show you how to find the 2 small matrices whose product is the big one. And for that, we're going to use features. So a feature in a movie can be anything. It can be, for example, if the movie is comedy, if it's action, maybe if it's drama, scary. Other features can be, maybe does it have a big boat? Does it have a sad dog? Is Meryl Streep on it? Or does it have a sexy Canadian guy called Ryan? It can be pretty much anything we want. So let's look at, for example, 2 features, comedy and action. And so now I'm going to introduce the dot product. And the dot product is a way to guess a rating based on how much a user likes comedy and action and how much a movie contains comedy and action. So let's say we figured out somehow that Anna likes comedy and she doesn't like action. And I'll tell you later how to figure this out. And now let's say that we've managed to rate every movie based on how much comedy and how much action they have. So let's say we figured out that Mall Cop has a rating of 3 in comedy and 1 in action. So what we're going to do is from here, we're going to figure out how many stars Anna gave Mall Cop. So since Anna likes comedy, then we're going to take the 3 of comedy. And since Anna doesn't like action, we're going to forget about the 1 of action. And we're going to say that Anna gives 3 stars to the movie Mall Cop. So let's do another example. Let's say we figured out that Betty does not like comedy, but that she does like action. And Malcup again has 3 for comedy and 1 for action. So this time we're not going to care about the 3 of comedy, but we're going to add the 1 of action, and Betty's going to give 1 star to the movie Malcup. And let's just do one more example. Let's say we figured out that Dana likes comedy and likes action, and Sharknado happens to have a rating of 1 for comedy and 3 for action. So what we do is we add the 1 and the 3 because she likes both comedy and action, and so the movie Sharknado, she's going to rate it with 1 plus 3, which is 4 stars. So let's look at the 2 tables. The table in the left is the scores for each movie based on comedy and action. So for example, the first movie has 3 in comedy and 1 in action, and so on. And the second table has the preferences of each person. Do they like comedy and do they like action? So for example, Anna, the first row, she likes comedy and she dislikes action, and so on. And so I'm going to repeat the calculations from the last couple of slides. If we look at Anna and how much rating she gave movie 1, well, we look at the movie 1 row, which is the first one, and that gives a 3 when it comes to comedy and a 1 when it comes to action. And then we go to Anna's row, which is the first row, and we say, okay, well, Anna likes comedy, dislikes action, so we're going to add the ones that appear with a yes. So that's a 3, because we add the 3 and we don't add the 1. So Anna gets 3 stars, gives 3 stars to the movie 1. And let's do Betty with movie 1. So we look at movie 1 row, that's scores of 3 and 1. And at Betty's row, that's a no for comedy and a yes for action. So we get the following. We don't add the 3 and we do add the 1. And so we get 1 star for movie 1. And finally, for Dana and the rating that she gives movie 5, well, we look at the movie 5 row and at Dana's row, and she gives a 1 plus 3 because we're counting both the comedy rating and the action rating. So she gives a 4 to movie 5. If you've seen dot product, that's it, right? And basically for each row in the left table and for each row in the right table, we can actually come up with a movie rating. So basically for every movie and for every user, we can come up with a rating like this. So we're able to fill every single entry on the table on the right by combining the corresponding row on the movie feature matrix and on the user feature matrix. So what we did is we expressed that movie on the right as a somehow as a product of the two matrices on the left. So what we did is factorization. Basically, we expressed the 24 as a product of a small 6 and a small 4. So now we expressed a big matrix as a product of 2 smaller matrices. And the way I like to see it is like this. So I have the matrix where the rows are users and the columns are movies in the middle. And on top we have where the columns are movies and the rows are features. And on the left we have one where the columns are features and the rows are users. And so for example, if you want to look at any entry in this matrix, for example, this 4 for Betty and movie 3, well, we obtain it by doing the dot product of this column, movie 3, and this row, Betty. And as you can see, it's a 1 and a 4, but Betty doesn't like comedy and does like action, so we only add the 4 and we get a rating of 4. So that's it. That's basically how matrix factorization works. And notice that the dependencies that we found previously among the rows and columns are found here too in an easier way. Remember that the first row and the third row were the same? That's because the preferences of Anna and the preferences of Carlos are the same. They both like comedy and do not like action. So that equates to the fact that the rows are the same. In the same way, remember that the first movie and the fourth movie had the exact same ratings from everybody because the columns were the same. That is because both movies have the same scores for comedy and action. If you look at the top matrix, they both have 3 for comedy and 1 for action. And this can be even more intrinsic. Check this out. Remember that the sum of the two rows in the middle was the bottom row? That is because if we take Betty's preferences and Carlos's preferences and put them together, they become Dana's preferences because Betty likes action and Carlos likes comedy and Dana likes action and comedy. So that's why the rows, second row plus third row is equal to the fourth row. And if you remember, the average of these two columns was this column. And that's because in the top matrix that happens. The average between 1 and 1 is 1, and the average between 2 and 4 is 3. So like the third movie has scores in comedy and action, the average between the second and the fourth movie. So in a nutshell, that's what matrix multiplication is. It's basically expressing a big matrix as a product of two smaller ones where we use some kind of features. And as we saw, the dependencies between the small matrices and rows and columns actually translate to dependencies in the big matrix. So this matrix factorization has a lot of benefits. One is storage. This is not the main benefit, but it actually comes for free. Basically, if we want to store the big matrix in the middle, all we need to do is store the one on the top and the one on the left, and we save a lot of space. Here's not so obvious, but if we look at really big matrices, we actually do save a lot of space. So let's say we have a big matrix of 2,000 users and 1,000 movies. So let's think. And feel free to pause the video and guess the next number that's going to appear. But how many entries are in this matrix? Well, the answer is 2,000 users times 1,000 movies. So there's 2 million entries, 2 million ratings. And if we manage to factor this as a product of two small matrices, one of, say, we have 100 features and 2,000 users, and one of the same 100 features and 1,000 movies, then how many entries do we have now? Well, in the top matrix of 2,000 by 100, we have 200,000 entries, and in the left matrix of 1,000 movies plus times 100 features, we have 100,000 entries. So in total, we have 100,000 plus 200,000, which is 300,000 entries versus 2 million that we had to store at the beginning. So it's a huge saving of space. And again, if we want to find any entry in the red matrix in the middle, for example, this one, what we do is we take the dot product between the corresponding row in the left matrix and the corresponding column in the top matrix. Some people like to see it as matrices, and some people like to see this as graphs. So we can see this as graphs as well. For example, here are our 4 users, and here are our 5 movies. And every rating is the label of every edge from a user to a movie, right? Because each user gives each movie 1 rating. And that's a lot of edges. But if we actually put 2 features and instead we have that each user gets associated to each feature in some way, either they like that feature or not, and each feature gets associated to each movie in terms of like a number that gets associated, like how much comedy does this movie have, how much action does this movie have, then we're actually saving a lot of space because the left one has a lot of edges and the right one has much less edges. In this small case, it's not a lot of space we save because the left one has 20 parameters. There's 20 edges, which is 5 times 4, whereas the one on the right has 18 because it's 4 times 2 for users times features and 2 times 5 for features times movies. So it's 8 plus 10. So there's not a lot of space. But if we think about it, if we had 2,000 users and 1,000 movies, then we had 2 million parameters. This is the same calculation we did before, 2,000 times 1,000 parameters. And if we were to split it between features, users features and feature movies, and we had, say, 100 features and still 2,000 users and 1,000 movies, then in the top, the green edges, there is 200,000 of these because it's 200 users times 100 features. And the bottom, there's 100,000 because 100 features times 1,000 movies. And if we add those two, we get 300,000 parameters. So in summary, on the left, we have 2 million parameters, and on the right, we have 300,000 parameters. So it's a lot of space that is saved. But of course, The reason we do this is more than saving space, is for actually predicting the user's rating of a movie. We're gonna see that in a little bit. But the question we're gonna answer now is, how did we find this factorization? Like this is something maybe a human can eyeball and say, okay, maybe this person likes comedy, this person likes action, but in reality, the computer doesn't know this, and the computer just has to figure out, first of all, what the features are, and second of all, what are the features that people like, and what are the scores that people that movies give to a feature. So this is not obvious. So for that, we need machine learning. So this is what we're going to answer now. How to find the right factorization. So let's say this is the user, or this is the person, the machine learning professional, and machine learning professional is thinking of a matrix, and then a computer comes in and tries to factor this matrix. So the computer says, okay, is your matrix the product of these two small ones? And the human says, nope. So the computer goes back and then comes back again and says, actually, is your matrix a product of these two other matrices? And the human says, oh, still no. So the computer goes back, does some calculations, and comes back and says, hey, is your matrix a product of these two? And then at some point the human says, you know what, that's close enough. Because in machine learning, you never say, that's good. You always say, yeah, that's close enough. So that's kind of the process in most algorithms in machine learning. You try, get a little better until you get something good. I can be more specific here. So what we're really doing is called gradient descent. And gradient descent is used widely in machine learning, and this is how it works. So this is the point where we want to get. Our matrix is in the middle, our target matrix, and the two factors are the one on the top and the one on the left. So the two matrices whose product is supposed to be the one in the middle. So notice that I've made a small change. I don't have the check mark and the X anymore. I have a green 1 and a red 0. So the 1 is corresponding to the check mark and the 0 is corresponding to the cross, and they work the same as before. So how do we get to find that matrix on the top and that matrix on the left, which are ideal? Well, we start with some random values and then get better and better and better until we hopefully get to something pretty good. So let's start with random values. Here we have a matrix with random values on the left for the user feature matrix, and a matrix with random values on top for the movie feature matrix. And notice that I don't have comedy and action anymore. I just have two features, F1 and F2, because all we know is that there are some features. Maybe we can describe them, or maybe not. Maybe the computer just knows that there are certain type of movies and certain other type of movies, and that's it. And the question is, how do we pick that two? Well, that's called a hyperparameter. So that's just we try a few different numbers and see how we do better. But for now, let's try to find it with two features. So the product of these two matrices, we're going to put it here. And what's the product of these two matrices? It's going to be this one. So let me show you a bit of how to find these numbers. It's basically the same as before, except the dot product is now a little more general. So how do we find, for example, this 1.44? Well, it's a dot product of this column and this row. And what we're going to do, dot product is we're going to take the corresponding elements and multiply them and add them all together. So we take, for example, the first entry on both, the 1.2 and the 0.2, and multiply those. And then the second entry is the 2.4 and the 0.5, and we multiply those. And then we add them together and get 1.44. So that is the dot product. Notice that if you have a 0 and a 1, like before, the dot product is really saying, I'm going to add the 1 corresponding to the 1 and not add the 1 corresponding to the 0. So it's the same thing, except a little more general. And so we do that for every entry, and we obtain a matrix full of entries. It's probably not the ones we want, but we're going to see how far we are. So we're going to compare it to the original matrix, to the target matrix, the one we want to find. We're going to look at them, compare every entry, and see how we're doing. So we compare that 1.44 on the top left corner with this 3 over here, and we say, okay, The computer comes with the 1.44 and says, how am I doing? And we have a 3, and we say, well, I guess you're doing all right, but you're not exactly at my 3. What do we need to do to get this 1.44 closer to the 3? Well, we need to increase the 1.44. So what do we do to increase the 1.44? Well, we need to increase these values by a little bit and these values by a little bit. And so let's say we increase them. Let's say we increase them by a little bit. So the 0.2, let's say we turn into 0.3, etc. So here we increase the values a little bit. Now we have 1.4, 2.5, 0.3, and 0.6. We find the dot product, and now we get a 1.92. So that's closer to 3 than 1.44. So, okay, let's move on to the next entry. The next entry now we calculated, and it's 1.83. We did the dot product of these new values. And 1.83, well, we're going to compare it to this 1 over here, and it turns out that it's too high. We want to get to a 1, and we have 1.83. So what do? Well, we need to decrease this. And to decrease this, we decrease the entries on top and the entries on the left. So we decrease them by a little bit and then move on to the next entry and then move on to the next entry. And then we do this repeatedly and repeatedly. And believe it or not, eventually we get to something pretty good. And with some luck and a lot of computing power, we get to something we want. Now, I didn't say how much we increase or decrease, right? I just said a small value. So how do we know the small value? Well, now we need to do some calculus. So what we need to do is we're going to define an error function. And an error function is basically a way to tell the computer how badly it's doing. So it's not enough to just tell it, hey, your matrices don't work. If we're able to quantify how badly the matrices don't work, like if we say, okay, the error is 10 or 5 or 2, then the computer knows a little more because it knows how to decrease that error function. And this error function concept is used widely in machine learning. Most algorithms have one. So the way it works is this. I mean, before we had that the computer asks you how he's doing, and the user says, nope, you're not doing well. Now the computer comes in with 2 matrices, and we say, hey, you were wrong by 10.3, for example. And the computer comes in with a slightly better matrices, and we say, hey, you were wrong by 5.32. And then it comes with better matrices and say, hey, you were wrong by 1.23, and then maybe that's small enough, so we're happy. So we say, okay, I'm going to take that as the answer. So now I'm going to show you how to find this error, how to define an error to tell the computer how far it is from the actual answer. So let's recall that this is where we want to get. That's our matrix and our target matrix in the middle, and the factors on top and on the left. So again, let's look at the same random numbers we had before and the entries that we get in the matrix on the left. So we're going to compare this 1.44 with this 3. How do we compare 1.44 with a 3? Well, the difference seems like a right place to go, right? 3 minus 1.44 or 1.44 minus 3. It's hard to tell which one is better because one is positive and the other one is negative. So actually, to get rid of this ambiguity, we're going to take the square of the difference. So 3 minus 1.44 squared, that's always going to be positive, and that's going to tell us how far these numbers are apart. So that's it. That's the difference. That's an error between the first 2 entries. And then we move on to the second entry, and we do the same thing. We take the square, the difference of the squares, 1.37 minus 1, or 1 minus 1.37 square, and then we move on to the third entry, and so on and so forth. And so the error is simply going to be the sum of the squares of the differences of each pair of entries in the matrix, each corresponding pair of entries. And now there's an error. And so how do you decrease an error? Well, this is a common method known as gradient descent. And I won't get into too much detail in this video, but there's other videos in this channel where we can look at gradient descent. What you do here is you decrease the error by taking the derivative of the error and walking in that direction. So what we want to do is we want to find this derivative, and this derivative is going to tell us by how much we should go up or down in order to decrease the error the most. So that is the method called gradient descent. And so what we do is we apply it repeatedly on all these entries, and eventually we get the right numbers on the matrix on the top and the matrix on the left in order to find the right factorization. So that's pretty much it. That's the matrix factorization algorithm. Now let's look at how to use this, right? Because we saw that it helps us, that matrix factorization helps us with storage, but it also helps us with what we really want to do, which is predict ratings. So this is how the Netflix matrix looks. It actually doesn't look like the one we saw at the beginning because not every user rates every movie. The matrix is actually very sparse. It looks like this. And what we want to do is we want to fill in the blanks. So we take this matrix and somehow find a way to factor it as something on top and something on the left. And the way to factor is the same as before. We take the difference and use gradient descent. And the difference is now just this, the difference of the squares of the entries that we have. We don't take the entries that we don't have. But anyway, once we are able to find these two matrices that approximate whose product approximate this matrix, then we can actually fill in the blanks by taking the dot products of rows and columns. So we fill in the blanks like this. So these white ones are the predicted ratings for each user and movie that don't exist yet. And now what do? Well, if, for example, Dana comes in and she hasn't seen movie 1 and movie 3, then which one do we recommend? Well, it turns out that between movie 1 and movie 3, the highest predicted rating is movie 3, which is 5. So we recommend movie 3 to Dana. And that is pretty much it. Thank you very much. As usual, yeah, you can find me on Twitter, Lewis Likes Math, and this is my channel. And you can also find a blog that I have on GitHub where I put the occasional article on machine learning. And if you really like what you saw, I actually teach these courses at Udacity. I teach machine learning, deep learning, artificial intelligence, etc. So you can go take a look at them. There's some really interesting ones that are free. For example, if you go to the Udacity app on the phone, check on the top, you're going to see a free course called Intro to Machine Learning, and there's another one called Intro to Deep Learning. This only works on mobile. So take a look at them. They have a few lectures that I teach there, and I hope you enjoy them. So thank you very much, and see you in the next video.